Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thank you for coming. It's great to be here. I think by now it's pretty generally agreed that interdisciplinary research is going to be a very important aspect of scientific research in many fields. And what I would like to do today is to give you a perspective about interdisciplinarity from the perspective of theoretical computer science. And I believe that to some extent it also reflects the general features of interdisciplinary research. So the question we really want to think about is that what is interdisciplinarity and how does it become interdisciplinary? So let's begin from the history of theoretical computer science as a subfield in computer science. And to some extent, that theoretical computer science, like many other mature scientific fields, itself is a result of evolution from many disciplines. So to some degree, it is always interdisciplinary in nature. And so let's look at the story of theoretical computer science. It can be regarded as a tree. And at the roots is the effort by Alan Turing and other pioneers in theory of computation. They asked the question, what does it mean to compute? What's the meaning of computing? And so what they focus on is the question, what's the mathematical model of computation? And now, so this is really the core of theoretical computer science in its original form. And through the many, many years, the 60, 70 years of development, we have many important developments, including, for example, the theory of NP-completeness by Cook, Karp, Levin, and etc. And however, theoretical computer science is not just this line of thinking about what does it mean, what's the model of computation. And there are many inputs in subsequent years from other disciplines. And each time it brings in new problems, a new perspective, and most importantly, new talents that at first, at some stage, one might as well say that it's an interdisciplinary area of research. But gradually it matured and really has now become an integral part of theoretical computer science. So for example, Don Knuth bring in the question that involve the more practical side of computing and emphasizing the study of algorithms and data structures. And the famous Kolmogorov in bringing the idea of algorithmic information. And so it's not just the subject, the concept that's bring in by these great scientists, but it's also they have produced some very important students who have made a difference in the field. So Kolmogorov, for example, Levin and Rasparov, they all have become really pillars of the field that come from the Kolmogorov school. And now I think that everyone knows Paul Erdős and brings the Hungarian combinatorics, the whole school. There are many, many talented Hungarians who came into the field and solved many of the unsolved problems in theoretical computer science and have since become the standard tools in theoretical computer science. And of course, the Claude Shannon, the information theory, has a big influence on theoretical computer science. And now we're coming to more recent times in the last 30 years. And the interaction between computer science and information theory and community brings in the idea of merging the Shannon's information theory and Alan Turing's computation theory and created the field of modern cryptography and the influence of biology manifested about 20 years ago because computers are become more and more important for solving biological problems. And then the quantum computing makes a quantum information interdisciplinary between physics and computers, and the algorithmic game theory, it's a very important active field, interdisciplinary between economics and computer science, etc. And so the last three, I think that one might really call them interdisciplinary area. And my hope is, and I believe that over time, they would become such an integral part of theoretical computer science. Then I don't mean that we would own this area so that it's not part of physics or biology, but I mean that it would not be, it will be just as common as people who work in combinatorics and in theoretical computer science. And now, stepping back and thinking about this pattern from a more general view, that now how does the computer science itself, what's the story of computer science? And we all know that computer science, in some sense, has always been interdisciplinary. Starting from the very beginning, we know that computer science has important applications to physics and biology and engineering, and but usually what it means is that in those disciplines, they need to solve their problems using computers merely as a tool. They would like to get numbers. And so one might schematically draw that in the earlier years, those fields, if you look at their core, the core areas don't intersect. It's just that they need to use computers. And however, one thing that dramatically changes is that we have found, especially in theoretical computer science in recent years, that these cores, for one reason or another, have found each other. So there is a significant intersection in some parts of the core of those disciplines with computer science. And therefore, to solve their problems, it's not just enough to tell them what the best algorithm is for solving their problem. But actually, in many cases, the collaborations between computer scientists and these other fields become an integral part of the progress of the field. So that all sounds very abstract. So, for the rest of the talk, what I would like to do is to give some examples. And now, before showing you the examples, let me first set some benchmarks. So how do we know the results of in a certain research is interdisciplinary? I'm just going to focus on three indications. The first one is that it would involve researchers from computer science and from the other discipline. So looking at co-authorships. And the second is that they will be published, at least from the theoretical computer science point of view, the results are published in non-core theoretical computer science journals or conferences. And the third thing is that getting published is not enough. Are they of real significance to computer science and other fields. So I'm going to keep in mind there are 3 benchmarks, and I think as a crude first cut at differentiating research, which merely involves computers, and something that is deeper. So I would like to look at 3 examples. One is involve the computer science and economics. One involves computer science and physics. And more generally, there are topics that are so universal, and they are not just computer science in one discipline, but actually even philosophy. So let me first look at the case of auctions, which is about the interaction between computer science and economics. Suppose you have an item for sale. Suppose you have an apple, and the problem is that how much are people willing to pay? And so we can certainly ask people, I mean, how much would you pay for it? And they will probably lie. They will try to get the best price they can. So the theory of auction is that how do we design the rules? How do we ask them so that people have an incentive to reveal their true values? So the auction theory really is a subfield of something called mechanism design. So for the market, you make a design on how the market would operate. And so this really says that under this paradigm, economists are engineers. So you would like to design an auction so that in equilibrium, we get the result that we want. And so the goals of the auction, the seller, which is the auctioneer, may have several different goals. The most common goals, one is to maximize the social welfare. And so what it means is that we would like the item to go to the person who values it most. So this is, it's from a global point of view, that's the maximum efficiency. Or from the seller's point of view, maybe I just want to maximize the revenue as the profit. And let's just look at 2 very simple of auctions. And let's consider you have one item, you have an apple to sell, and there are many buyers. Each one of them would seal their bids. And so when the seller opens the envelope, he sees all the bids. And then how do you decide who to give it to at what price? And the obvious natural solution is to do it called the first price, namely that you look at the maximum bids and you sell it to this guy and at the price that the person is willing to pay as stated there. And now that's seems to be a fair solution, but unfortunately it's very easy to cheat, because if I think that all the other bidders probably have a lower valuation than mine, then why should I reveal my true value? I should lower my value by a few dollars so that I can still get the item but at a lower price. So therefore, the first price auction is not an auction that is truthful. So in other words, people don't have an incentive to tell the truth. And another seemingly unnatural way of doing it is called second price, or it's called victory. And don't underestimate it. There's no price in it. And so what this does is to award the item still to the person who claimed that he valued it most, but charging at the price only at the second highest price. So now you can see that the second price auction has a distinct merit, namely that it's truthful, because if I value at something and I know that even though I know that all the other bidders have a lower price, there's no reason for me to put in a lower bid, because if I get if I lower it, I will still pay the same price. So the price doesn't depend on my action at this time. So the second price auction has the distinction being, firstly, it's truthful, and secondly, it also maximizes the social welfare because the person who deserves it most actually get the prize. And so let's think about this definition of a truthful mechanism. And this turns out to be a very profound concept. And so what is a good, great piece of work? What is great research? And it depends that you have one or more really critically deep concepts that are very important in applications or in aesthetics, and seems to be very natural, but it's not very easy to completely characterize. So truthful mechanism turns out to be this. So this is very similar to, let's say, the idea of the concept of computability. What does it mean for something to be computable? And now, even though it's something that can be said pretty simply, but it actually, nobody has exhausted the idea of computability, because computability makes computer science what it is. It has at least one unique idea that is absent in all the other sciences. And it turns out that the idea of a truthful mechanism also has this character. The more you read about it, the more you do research in it, the more you are fascinated by it, because turns out to be a really deep concept. And and now, so this solves the problem when you try to maximize the social welfare with a truthful mechanism. But how about in other models? For example, suppose you want to achieve revenue. You want to maximize the revenue using a truthful mechanism. Is there something simple that you can do? It's just like the second bit. And it turns out the revenue maximization problem, in some cases it's easy, but in some cases it's very deep. So suppose you want to sell, instead of one item, but you have k items to n buyers. And now the k equal to 1, the single item case, Meyerson gave a complete solution to this problem. And it's also a Nobel Prize work. It's a very beautiful work. And I cannot help but think about 1981. And I remember in 1981, I was at Berkeley. And at that time, cryptography was the rage of the time, at least in our field. And there are some really wonderful concepts in cryptography. And so little did I know that at that time, the economists have come up with something that is really profound and arguably have even more important than the computer science work that was fashionable at that time. And I mention this because this is a case. If you read the auction theory, if you read Meyerson's paper, it's exactly the kind of problem that we would love to solve. It formulated it, it's exactly a theoretical computer science problem. So there are cases. I think, how does things become interdisciplinary? In some cases, it's a gradual merge, because you need the other discipline to make your things work. But this is a case where they are the same, even from the very beginning. The motivation may be different, but the actually it's exactly the type of question. And if you have more than one item, if an apple and an orange you want to sell, then the problem is really an open. And there are single mechanisms, such as you just do it separately, or you can sell them as a single bundle. As a bundle, the idea is just that you can either get both items or you get none at a certain price. So selling one item, the seller has one item and has a partial knowledge of the buyer's interest, and how does it maximize the revenue. So if you set the price at P, then the expected revenue is P times the probability that the buyer would accept it. So therefore, this is the expected value. And so all you need to do in this very, very simple case, just one item, one buyer, is just you should set the price that maximizes this expression. Okay. But even for one buyer, if you want to sell 2 items, then it's difficult, even if these 2 items have a similar characteristic. So the natural way is to say that I just sell each item optimally, and however, you don't get the best algorithm. So for example, if you have item values which have each item has an equal probability to be worth $1 and $2 to the buyer, if you sell them separately, then the optimal value is going to be equal to 1. You can set the price to be either 1 or 2. You get the same expected revenue. However, if you sell it as a bundle, you say that you either buy both the apple and orange at price $3, or you're not going to get any. If you do the calculation, you can see the revenue is bigger than if you sell it separately. And now, actually, things are much more complex. If you look at some simple examples, let me just go to the very last one. If the distribution is so that its probability 1/6 to be $1 is worth $2 with probability of half, and to be worth $4 at probability of third, then the optimal solution is a very complex combination. It says that I would offer the buyer 2 alternatives. Either you can get a lottery to get one single item for $1, but the lottery has only 1/2 of the probability to succeed. And the second alternative is that you can get both for $4. So this is the unique solution that works optimally for this. So that all this indicates that this truthful mechanism is a very profound concept. And even now, we really don't fully understand how to sell to one seller and with just 2 items. And but let me show you how the added value that the input from computer science can get you. Okay, so let me just write down the notation. The maximum revenue is from selling from items in a set. Okay, and so the question is, so you can ask fundamental questions like this, saying that how much is it better if you have an auction where you sell both items at the same time, compared with just selling them separately? And it's a question that's very natural and very simple to ask, but the answer is not obvious. And now in 2012, Hart and Nissan showed that what you would expect, that you can make more money, but not too much more than selling them separately. And the Hart and Nissan also show that if you sell them separately and you sell them as a bundle, there are some mathematics that you can analyze it, and how much does it differ from the optimal. And a follow-up paper by Li and Yao actually pinned down those ratios. And very recently, Babayev by the way, from Microsoft Research, they had a wonderful result. They showed that actually, if you sell separately and you sell a bundle, and you look at the better mechanism of these two, then you actually achieve the best optimal value to within a constant. And very soon, there is quite a general extension, and study the general case with n buyer and k item, and come up with a lot of insight into the problem, kind of following some of the leads that were presented in the previous papers. And in particular, it shows that the optimal revenue under the Bayesian or dominant strategy, they are equivalent up to a constant factor. So this may not make sense, but these are the type of question that the economists have been asking, and I think, it's only really by putting some of the computer science methodology that is possible to get this. And it's not important exactly what these results are. I just want to highlight the benchmark that I said earlier. Hart and Nissan. Hart is an economist, and Nissan is a computer scientist. So together, they initiate this very fruitful line of research in recent years, and they published a paper in a conference called EC, and it is a conference that's is designed to be cross-discipline. If you look at the program committee members and the students, they come from both economists and computer scientists. And now the publication venue of the follow-up paper is in the proceedings of NAS. So it's not really a theoretical computer science journal. And also, if you look at the most recent, the last result on the page here, I think these results are I think the economists will be very interested in knowing results of this kind. So the second question I like to example is quantum information. And now, replicating information, such as making Xerox copy of digital documents, has diverse applications. Now, the question is that is it possible to have a Xerox machine that can make a copy of not digital documents, but actually quantum documents and quantum objects? And now we know that it's not possible to do the strict copying, and so there's a no-cloning theorem which says that if you want to design a quantum machine that would take an input state phi and you want to produce 2 copies of it, then this is not allowed because of the constraint in quantum mechanics. And this is an important insight because this really is the basis for the security of quantum cryptography. But in the physics community, for 20 years, they are very interested in how do you get around the no-cloning theorem. Is it possible to clone a quantum object approximately or probabilistically? And many cases, special cases have been studied. But what about the general rules? It's a general theorem that tells you what limits how many really good copies you can get for a quantum state. What are the ultimate limit? And it turns out that there's a quite good, elegant solution to it. So let's just imagine you have a process that would you take n copies and you would make an extra delta n copies. And so you would like the replication to be reliable so that the copies are very nearly perfect. And a recent result shows that for a set of states under certain continuous symmetry, then the replication, we know exactly what the limit, how many extra reliable copies you can get. And if you restrict yourself to deterministic processes, the extra copies you can produce is sublinear in the original copy. In other words, you can produce a large number of extra copies that are very faithful. And now, however, if you allow yourself a probabilistic process, and then it obeys something called the Heisenberg limit, and it turns out that it's possible to produce. It's quite counterintuitive. You can produce nearly a quadratic number of copies, and that actually is the best you can do. You cannot do anything better than that. And this is a paper published by 3 authors, and so Chirabella is a physicist in our institute. Yan is a student of his. And so, so it's a collaboration between a physicist and computer scientist, and it's published in a journal, Nature Communication. So it's not a journal of theoretical computer science. And now, how does this look at computer science? Why is it that computer scientists actually would also be very at home with this question that physicists are interested in? Because the cloning of photons can be modeled as a computational geometry problem in a high-dimensional place. And also, this problem is very similar to generating almost identical keys in cryptography. And now, so those are two examples of marrying computer science with economics and physics. And now, let me find more partners for computer science. So this one is really I think people are interested in from very ancient times. And now, it's very important, as reported in New York Times, that in 2012, the researchers found a fraction of the public keys in a database. They are not randomly generated. So even though we advise them to generate randomly, but actually, in fact, people don't generate those keys randomly. So it will be possible for someone to figure out the secret key and to decode sensitive online information. And so the question of randomness is something that have been interested, I think that starting with philosophers asking, is the universe random? And now, as a science, statisticians have been interested in it for a long time, and it's a statistical test space. And in the 1980s, because of cryptography, computer scientists become interested and put it on using a different foundation. So it becomes really important for the progress of cryptography. And now, in the last 15 years, the physicists got interested in this question. So the question is that if you are allowed to use quantum processes, can you get much better, much stronger randomness? And so that if the physicists generate, using a certain device, generate to you a certain string of random, claimed to be random numbers, can you actually certify? Can it be certified as really truly random without any complexity assumption? So this would be unbreakable, and if you assume the nature to be quantum. And now, so that goes beyond just the philosophical questions and also the application of generate cryptographic key. And a hot topic in quantum cryptography among the physics community is about device-independent quantum cryptography. What it means is that in quantum cryptography, you have to use physical devices made by some companies. And suppose you don't trust the company. Is there a way so that you don't have to trust the company? If it works not as specified, you have an easy way to know that it doesn't work as specified. And now, the concept of the device-independent quantum cryptography was raised in a computer science theory, computer science conference in 1998. And, but it became very fashionable in the last 10 years. And eventually, a group of computer scientists, and I think Unger probably is a physicist, and they have made great progress on this problem. So eventually, after their paper, people have found ways to solve the problem completely. So they published their paper in Nature last year, and the idea is to make use of the certification process, the quantum-based certification, and made it possible for people to design device-independent quantum cryptography. So to conclude, when you think about all these examples, we think one can conclude that the reason that it's possible for different fields to have a chance to work together in many ways is because they have certain things in common. And for example, the sciences generally has a methodology. You observe the phenomena, you develop theory, you test them, and you refine the theory and further test, and so on. And now, for many years, computer science looks more like mathematics, and therefore, by this criteria, it doesn't satisfy to be a science. But however, in recent years, especially with the emergence of internet phenomena, and it's important to observe the traffic and the characteristic of the network. And so computer science gradually has a wing that would need to adopt this methodology in order to make progress. You have to observe what the patterns of traffic are. You have to use them. You have to develop theory. You have to use them so that you can design efficient networks. And you have to test your theory, etc. And concretely, this methodology, they all use a lot of mathematics and algorithms, and some of the key concepts that are shared by all sciences involve probability, complexity, approximations. And there's another reason that one can have subject of common interest is because the common abstraction actually, if you look at some of the hottest problems in different fields, they actually are the same problem with the same abstraction. They are just different manifestations, and they have different aspects that one wants to emphasize. So for example, the many-body systems is undoubtedly, this is the trend of development and the hardest subject facing everybody. So in physics, people are interested in condensed matter physics, which is a many-body system, and you like to understand how things behave under different laws and under the natural law. And in computer science, people like to understand what's the behavior of social networks. And in economics, people want to understand if you have the economic incentive, how do a large economic system behave? So all these are terribly important problems, and they are common abstraction. And I think that the full, I think a full interaction between all these researchers, they're going to lead to progress in each other's fields. And finally, there are universal topics that are independent of any utility. The concept of what it means to be random, what is the nature of information. These are the things that will be forever investigated and form possibility of collaboration between different fields. And so now, in theoretical computer science, actually, in recent years, it's starting to take shape in the sense that interdisciplinary research has begun to be recognized. And just to show an example, that the Simon Institute at Berkeley is a institute that is constructed explicitly for applying theory of computation to different disciplines. And here is an anatomy of the program on how they are running. And they have designed their space in a very efficient manner, so enable people to interact among different fields. And now I'm putting an ad for our institute, and we have established actually 3 years ago, and we're starting from 3 faculty, and now we have 20, and we have science and we have physics, and I think that we are one of the few computer science institutes that actually have physics labs. So I think that the net worth of our physics lab is at least 10 times of the assets of our computer facilities. And so here is of our our laboratory, and we have just got some new space in 2 floors in Tsinghua. So I think interdisciplinarity, it's certainly, I think that it has come of age. I think that certainly in China, it also starting to take shape. Thank you very much.